Okay, so we'll now talk about complexes, and in particular simplicial complexes, which are a way of triangulating a topological space, and that's going to end up being one of the fundamental objects we work with. It's like in this class when we go about trying to compute certain types of topological invariants. Okay, so one way, again, there are of course many ways to represent topological space, but one possible way to represent a topological space is to decompose it into sort of simpler pieces in some sense, or simple pieces. Okay, so we refer to such a decomposition as a complex if the pieces are topologically simple let's just say they're topologically trivial. Okay, and their intersections are lower dimensional pieces of the same type. Okay, and in particular we're going to focus on what we call simplicial complexes. So as the name implies, this is going to consist of collections of simplices. Okay, and I'll talk about what simplices are. Okay, so let's try to first talk about simplices. Okay, so before we talk about simplices, we're going to introduce the notion of an affine connection. Affine combination of points. Okay, so let's say we have k plus 1 points. So let u0 all the way up to uk be in some, say, d-dimensional Euclidean space. Okay, and a point x, which is some weighted combination of these other points, lambda I ui, right, is an affine connection, affine combination. Okay, of these ui's. Okay, if the sum of the weights is 1. Okay, all right. So you can look at the set of all possible affine combinations of this set of k plus 1 points, and that gives you what is called the affine hull of these k plus 1 points. Okay, so the affine hull is the set of affine combinations. Okay, and then this is going to be a k-plane. It is a k-dimensional plane. Okay, if the k plus 1 points are what are called affine independent. So you might ask, well, what does one mean? It's like when one says something is affine independent, or the set of points is affine independent. So we know, for example, that if you're thinking of things like linear dependence or independence, right? What it basically means is that if you look at linear combinations, it's like of those points, and you have two different linear combinations which give you the same number or the same vector, right? That the only way it's like that is possible is if the coefficients in the expansion all agree. Okay, so we're going to do something similar to that. Okay. So what we mean by affine independent, right, is that so given two affine connections, affine combinations, I'm sorry. X equals the sum Li ui. So I'm going to omit the index here just for simplicity, but it's sort of understood here that I'm summing from I equals to 0 to k. Right. So given two affine combinations, x equals to y, right, if and only if lambda I is equal to ui for I equals to 0 all the way up to k. Okay, so this is of course compatible. It's like with what we think of. It's like when we think about the notion of linear independence, right? So of course you might remember that when we discuss linear independence, it's sometimes possible to express it into the question of whether or not it is possible to construct a non-trivial linear combination of the vectors such that it adds up to 0. So you can't really do this in the affine setting because, of course, it's like you have the constraint that the sum of the coefficients is 1. So so it's not so that notion of linear independence and independence doesn't really apply here. But this idea of unique representation still holds. Okay. So you can relate affine independence to linear independence in the following way. Okay, so you have this set of points u0 to uk. Okay, so you can construct it like out of that set of points k vectors. Okay, so the k plus 1 points are affine independent if and only if the k vectors, where you sort of pick a distinguished point, let's say u0, so you construct the k vectors ui minus u0, and then I now goes from 1 to k, are linearly independent. So in RD, for example, right, you can have at most d linearly independent vectors which means then that you can have at most d plus 1 affinely independent points. Okay. All right. So this gives you this notion of affine. It's like combinations, affine hulls, affine independence. Okay. So there's the concept. So we haven't really gone to the question of simplices yet. Okay, so what happens with simplices are that in addition to the condition that the sum of the coefficients is 1, you also have a condition that all the coefficients are non-negative. Okay. All right. So let me maybe erase this. So in affine combination, x equals the sum of lambda I mu I. Again, the sum is from I equals to 0 to k. Is a convex combination. If the lambda i's are all non-negative, right? And again, of course, it's like it also has to be the case that the sum of the lambda i's is equal to 1, because it's affine. Okay, then the convex, well, so this is what's called a convex combination. Okay, then the convex hull. Right, as you might expect, then is the set of all possible convex combinations. And now we're ready to talk about what a simplex is. So a k-simplex is the convex hull of k plus 1 affinely independent points. Okay, and we denote this by following. So let's say this simplex is sigma. So sigma is the convex hull of a bunch of points, u0 all the way up to uk. Okay. Then, so when that happens, we say that the ui's span the simplex sigma, and the dimension of sigma, which is denoted by dim of sigma, is nothing more than just k, which is 1 less than the number of vertices. Okay. So, all right, so what do these things correspond to? Let's look at a bunch of simple examples. Okay. So if you just had one point, right, the convex combination of that by definition is just at one point. And this is, of course, a zero simplex, which we call vertex. Okay, zero simplex, which is called vertex. Okay, then if you have 2 points, right, and of course it's like when you take the convex hull, you sort of fill in, it's like the line between them. So this is a 1 simplex. So this is, for example, u0, u0, u1. And this is obviously oftentimes referred to as an edge, right? If you have a 2 simplex spanned by 3 points, and this is obviously referred to also as a triangle. And then if you had 4, right, this is a 3 simplex. which is the tetrahedra. Okay, tetrahedron. All right, so now we'll continue with a little bit more notation having to do with simplices. Okay, so the first observation is that, of course, you have these simplices which are spanned by affinely independent points, and it's easy to realize that if you take a subset of affinely independent points, they are again affinely independent. Okay, so any subset of a set of affinely independent points is also affinely independent and therefore spans a simplex. Okay, so this leads to the idea of what are called faces of a simplex. So for example, if you have a triangle, it's like you might think of the edge, it's like as being one of these faces. It's like the three edges as being faces of that triangle. If you think of the tetrahedron, then there are a bunch of triangles in there on the surface, it's like which are again faces, but also all the edges and as well as the vertices, it's like which are there as well. Okay, so so let's try to be more precise about this. So a face of sigma, okay, is the convex hull of a non-empty set, subset of the UIs. Okay, and then we say that it's a proper face if it is a proper subset of all the UIs. Okay, so and of course what I mean by a proper subset is that it's a subset, it's like of a set, which is not the set itself. Okay, all right. So you can denote the fact that a simplex is the face of another simplex in the following way. So we denote that, say, tau is a face of sigma by tau is less than equal to sigma notation, and tau less than sigma if it is a proper face. Okay, so you can also ask whether, it's like if you're given tau, it's like which are the the simplices which have tau as a face. Okay, and we denote that relationship by calling them a coface, right? So if tau is a possibly proper face of sigma, then sort of the duality, the dual relationship is that then sigma is a possibly proper coface of tau. Okay. All right. Again, if tau is a face of sigma, then sigma is a coface of tau. All right. And if tau is a proper face of sigma, then sigma is a proper coface of tau. Okay. Okay. So now let's define a few additional operations on simplices. Okay, so you can observe that a K-simplex has 2 to the K plus 1 minus 2 proper faces. And you can see that because, of course, in order to construct a subset, it's like of K plus 1 points, you have to decide for every one of those points whether it's inside or outside of that subset. So each of those you have 2 possibilities, so it's 2 to the K plus 1. But of course, there are 2 extreme situations where all the points are in or all the points out, which corresponds to either the original set itself or the empty set. So you want to exclude those 2 possibilities. So of course, now with the K plus 1 minus 2 proper faces. Okay, so given those proper faces, then the boundary of a simplex denoted by BD sigma is the union of all the proper faces. Okay, so you have this idea of the boundary, it's like of a simplex. So again, it's sort of, let's think about what you have here, right? So say you have a triangle that's a 2 simplex. Okay, and that thing says that there are 2 to the 3 minus 2. Okay, so that's 8 minus 2, that's 6. And there are the edges, right? 3 edges, and they are the 3 vertices, so that's 6. Okay, so that's consistent with the enumeration there. Okay, and when we say it's like the boundary, it's like of the 2 simplex, this triangle, we're referring to the 3 edges and the 3 vertices, the union of these proper faces, if you will. Okay. Yes, and then we can ask, well, what happens? It's like if you have the boundary, of course, it's like the other obvious notion. It's like you want to introduce this idea of the interior. Okay. And the interior denoted by int sigma is really just the simplex excluding the boundary of the simplex. Okay. All right. So you have this notion of boundary and interior now. So so you might ask if you know that any point in the simplex, in the K-simplex, is obtained by this convex combination of these K plus 1 points, can we say something about when a point is in the interior, for example, just based on the boundary, just based on what are the coefficients in this representation? Okay, so point x, which is this linear combination, convex combination, ui, lambda I ui, right, is in the interior. Okay, if all the coefficients are positive. Okay, and otherwise it is on a proper face. Actually, more precisely, otherwise it is in the interior of a proper face spanned by the points with the non-zero coefficients, corresponding to the non-zero coefficients. Okay. So then it's like you can convince yourself that so this observation, if you will, sort of immediately implies that any point in a K-simplex is in the interior of exactly one of the faces. Okay. So that means that in particular, every point x in this simplex belongs to the interior of exactly one face. And that face is obviously, as we had said before, is the face which is spanned by the points corresponding to non-zero coefficients, right? All right. Okay. So that more or less, it's like gives you the basic operations. It's like which we'll want to work with when we're talking about simplices. And then the next step is to sort of talk about, well, gluing these simplices together in some sense, right? And that leads to this idea of a simplicial complex. So let me just stop here for now.